All right. Welcome, everybody, to Standing for Truth. My name is Donny Budinsky, and this is Sam. We are your hosts for tonight's exciting program. On Standing for Truth, we uphold the truth of biblical creation. And I am thrilled to have Dr. John Hartnett here, a cosmologist and physicist, to help us accomplish this valuable mission. Dr. Hartnett is going to reveal the many problems with the Big Bang Theory. If you believe in the Big Bang and you are an objective thinker, there is a good, solid chance that you will no longer believe in it after this comprehensive program.
That's right, Donnie. Dr. Hartnett is going to demonstrate that the universe is God's universe, and the empirical scientific data confirms the Bible and the biblical account of origins.
Sam, we are going to leave no stone unturned tonight. The audience is going to receive a thorough analysis of the major weaknesses in Big Bang thinking. And I'm excited. Sam, would you do us the honors of giving our guests here tonight a formal introduction for anybody who might be unfamiliar with who he is?
I'd love to. Dr. John Gideon Hartnett is an Australian physicist, cosmologist, and Christian with a biblical creationist worldview. He has a PhD with distinctions in physics from the University of Western Australia. During his research career, he worked at UWA and the University of Adelaide and published more than 200 papers in scientific leading journals, in book chapters, and in conference proceedings. He was a foundering director of the Australian startup, now commercializing his research on ultrastable cryogenic clocks. He has lectured around the world in churches, at conferences, and written extensively on biblical creation, most in terms of astrophysics, cosmology. He also blogs at johnhartnett.org.
In other words, Dr. Hartnett, you are more than qualified to be speaking on this topic. I am very excited to have you here, and I am thrilled to have what looks like will probably be a go-to video for those in our audience, those invested in the creation versus evolution debate, a go-to video that dismantles the Big Bang Theory in a comprehensive manner. Dr. Hartnett, I really appreciate you offering your time for tonight's program. How are you doing today?
Yeah, good. Thank you very much.
Awesome.
Thanks for having me.
My pleasure. My pleasure. We've been familiar with your material and your information and your dismantling of the Big Bang for years now. And so it is a real privilege to have this opportunity to get to talk to you and learn from you. And so to the audience, what our structure is for tonight's program, a cosmologist dismantles the Big Bang Theory, is we are going to be handing it to Dr. John Hartnett to give a comprehensive presentation addressing the Big Bang Theory. Now, as always, we do these live for many reasons. One reason is so we can interact and engage with your comments, with your questions. We love our critics and we appreciate our critics being here as well. So please, if you hear something that Dr. Hartnett may say in his presentation that you disagree with or you want to challenge, then feel free in a respectful manner to send in your questions, send in your objections, tag me either at Donny or at Standing for Truth. I'll save those and we will have a good interactive discussion after John's presentation. So with that, Dr. Hartnett, I'm excited to get into your presentation, and therefore let's hand it over to you. Thanks again for doing this, and the floor is yours, brother.
Thank you. Okay, so we're dealing with problems with the Big Bang, and before we get into it, I would like to highlight that in recent times there's been a lot of claims of successes with the Big Bang Theory, even people claiming successes with observations from the recent observations from the James Webb telescope. But really, a test of any theory is not the successes. It's actually the problems that the theory has. It's the contradictions, it's the inconsistencies. Because, no one uses the scientific method. But if they did, the point of the scientific method is that you look to refute the theory. You cannot prove anything in science, you can only refute. And so I'd like to, with that in mind, to deal with, sorry about that. To deal with this issue of science. And I make the claim that cosmology is not science. Dr. Richard Liu from the University of Alabama, Huntsville, he made the claim that cosmology is not even astrophysics because all the principal assumptions in this field are unverified or unverifiable in the laboratory. And he says that cosmologists have become comfortable with inventing unknowns to explain the unknown. So this is really important that we understand this, and I'll get into a little bit more in a minute, but science really is about our ability to interact with the experiment. I've spent a lot of time in research labs building ultrastable clocks is my main source of bread and butter, and we are able in those lab experiments, we're able to interact with that experiment. But you cannot interact with the universe. You cannot carry out an experiment on the universe. You cannot send a light ray out there or some signal and get a response back from a galaxy or galaxy clusters. You can't. And I don't mean to offend anybody, but actually cosmology is closer to stamp collecting. It's assembling masses of data, just like someone collecting stamps would collect different species, and cosmology is the same. It's observational, and it's collecting these various species at, say, different redshifts, looking at different galaxy types, morphology, and so on, and then trying to use those observations to test their particular theory. Well, if we look at the Big Bang as a whole, there are several observations, and that's what they are. They're only observations, which are explained using unknowns, as Richard Liu puts it. Galaxy redshifts, which is possibly one of the best evidences for the Big Bang, the Hubble relationship, the systematic increase in redshift out into space. But that is explained with expansion of space. Well, what is expansion of space? What is it? To argue that space expands, you would have to understand what that is. It's not what a lot of people think it is, that you have like a ball of gas that's exploding and the gas particles are all rushing away from the central point of the explosion. No, the concept of expansion of space is cosmological expansion, that the whole fabric of space, the cosmic substratum, if you like, is expanding and dragging the galaxies that are stuck in that space along with it. Well, we have no laboratory observation of any concept that you would call expansion of space. And possibly the second best line of evidence for the Big Bang is the existence of the cosmic microwave background radiation. Okay, that's an observation, but it's explained as the afterglow or some type of echo of the Big Bang, the initial Big Bang. How could you test that? Well, as I've said, you can't interact with the universe. So you're, again, subject to the collection of observations that you make about that radiation. And we can discuss a bit more about that in a minute. And then there is the issue of dark matter. Now, this comes up on all scales in the universe, but it started out in the 30s with Zwicky in the anomalous rotation curves of spiral galaxies. They didn't seem to obey the Newtonian law that as you go out from the center of the galaxy, the rotation speeds, or the speeds of the stars, and then later further out the gases, should decrease. But they seem to come to a sort of plateau to reach a constant speed, even on the outer edges of spiral galaxies where we can see no stars at all. It's just the gases that they're able to spectroscopically measure their motion. Okay, so dark matter is used as some type of a placeholder, if you like, for physics that we don't understand. And over time, it's been invoked on every scale in the universe, not just galaxies, but in stars, star formation, clusters, cluster formation, and on the largest scales in the universe. Even starting out right in the early alleged Big Bang universe in the first 10 to the minus 32 seconds after the alleged universe began to expand out of the singularity. Dark matter, or some form of dark matter, is assumed. In fact, it's necessary. And then number 4 here, the supernova type, this is type 1a, supernova observations are dimmer than they expected. And this came in the late 1990s, 98. Reese and the Redshift supernova team, another team, they determined to put back Einstein's very famous cosmological constant, because without it they couldn't explain the fit of their data, using the supernova as a standard candle to test the distance modulus. This is the distance determined from the brightness of a standard reference light source, or standard candle as they call it, and they found that they were dimmer than expected, and that by putting in the cosmological constant again, this time as some type of dark energy field, and sort of an anti-gravity force, then they could fit the equations without assuming some weird negative mass or something like that. And that then meant that the universe was not only expanding, but accelerating. And then the 5th item from Lou is cosmic inflation, also another unknown. Now, this idea started out really somewhere in the 80s, because in the late 60s, early 70s, the idea of the Big Bang nuclear synthesis indicated that monopoles, these are like magnets that have only one pole, they should be everywhere in the universe, but they were not observed. And then as time proceeded, other problems arose. Well, the flatness problem was right there in the late 60s, 70s, and that was that as we count galaxy distributions back then, it seemed like the universe was flat. That means it was Euclidean in space. And how do you explain that? And then the horizon problem, which came pretty much after measurements of the cosmic microwave background radiation, when they were able to measure the fluctuations across the sky in various regions across the sky, and it was too uniform. And that was part of another problem. Why was it so uniform? But the horizon problem arises from the fact that there's not time in the early universe for radiation from one part of the universe to mix up with radiation from the other side of the universe, which we're seeing here today, within the time frame, the alleged time frame of the universe, because it's limited by the speed of light. And people have proposed ideas of higher speed of light and various things like this, but cosmic inflation was the answer. That the early universe, the reason we see it so smooth, or reason why we can solve this horizon problem, is because what we see today in the visible universe was a very small region of space in the early universe that was rapidly expanded or inflated in size by some incredible factor, like scale factor increase of 10 to the 26. Look, it depends on the particular version of inflation, but in a very short period of time, 10 to the minus 32 seconds or 36 seconds or something after the initial expansion, you have this volume expansion of 10 to the 78 times in the universe. So all these problems that might have been because the initial Big Bang was hot and turbulent and lumpy, they all get stretched out. So what we observe today is only the very small section where the light was able to interchange and equilibrate in temperature, and therefore today we see a very uniform cosmic microwave background radiation, and it solves that horizon problem. So cosmic inflation actually was used to solve a lot of problems all in one foul swoop, but there's no direct, even observational evidence that it ever occurred. So these are 5 unknowns, and in a good experimentalist mind, you don't invoke unknowns to solve your problems. Now, occasionally new physics arises. So I grant that there's a potential for new physics, but then we should look for what that new physics is instead of inventing fudge factors in essence that we have no laboratory experimental evidence for. This is not just this issue of cosmology as science, I should say as operational science, has not been lost on many cosmologists. Here's a quote published in 2007 in Science journal. Charles Bennett is a cosmologist, and he wrote that researchers have measured the temperature variations in the CMB radiation so precisely that the biggest uncertainty now stems from the fact that we see the microwave sky for only one Hubble volume. That is, we only have one observable universe, and an uncertainty called cosmic variance. We've done the measurement. It's not going to get any better. So how do you test your theory on this one Hubble volume, on only this one, the observable universe that we have? It's not like you can line up a whole series of universes and you can test your statistics on thousands of universes to see if what we're claiming is true. And that's the limit of what cosmic variance sets. So the solution normally would be to do massive computer simulations and simulates thousands and tens of thousands of universes. But that then relies on the input parameters and generally the human bias, the bias of the researcher who already believes the Big Bang story. So this becomes an essentially it's untestable theory. Going on to this point further, what's his name? James Gunn from Princeton. He's one of the co-founders of the Sloan Digital Sky Survey. He said that barrier to knowledge, some argue, is cosmology's Achilles heel. Cosmology may look like a science, but it isn't a science. He said a basic tenet of science is that you can do repeatable experiments, and you can't do that in cosmology. And to be clear, that a repeatable experiment doesn't mean you repeat your observations with, say, the Keck telescope, or you do it with another telescope, or no. A repeatable experiment means you interact with that universe. You get a response by interacting like an experimentalist would do in a laboratory. In this case, you're subject to that stamp collecting, to making more and more observations and to see how they fit into your theory. But you can't prove your theory. It's impossible to prove. You can only ever disprove. So if you find contradictions with your theory, then those contradictions disprove it. Doesn't matter how many other observations you make that you claim are consistent with or strengthen your theory. If you can't explain the criticisms, the objections, then the theory has been refuted. Going on to another cosmologist, this time Michael Turner, he says the goal of physics is to understand the dynamics of the universe. Cosmology is a little different. The goal is to reconstruct the history of the universe. Cosmology is more akin to evolutionary biology or geology, he says, in which researchers must simply accept some facts as given. And this is the problem. This is what some people call historical science. Maybe the best analog is forensic science. Forensic scientists come on a crime scene and they have evidence available to them, might be fingerprints or DNA samples or footprints and things like this. They then try to reconstruct what happened in the past, but they have no access to the past. They can only put together a theory and see how the facts line up, but it's not experimental in the operational sense. And this is the same with cosmology. It's closer to evolutionary biology. We're lining up a whole array of different organisms in the fossil record and trying to sort out that and say this one evolved into this one. Geology is the same problem. We have no access to time machines. We can't go back into the past. And I would say, you know, some people will say, oh, but with cosmology, we're looking into the past. Actually, that is circular reasoning, because you are claiming what you're seeing is at some past epoch, but it takes your cosmology to determine what that epoch is. So it's circular reasoning if you have to assume your particular cosmology to be true to identify where you are in that past epoch of time. I like to use this illustration because it's like this is an elephant in the kitchen, or maybe it's in the observatory, and there's not a perfect metaphor here of the four blind men feeling different parts of the elephant and them getting different interpretations. but it's close because the case of cosmology, the astrophysical observations are essentially all the same, but different theories are presented to explain those same observations. So that's where the analogy is not quite right. And this problem is the problem of undetermination. Essentially, undetermination tells us that there are more theories that could explain the same cosmology or cosmogony, in this case, the origin of the universe, there are more theories than one, and therefore, how do you distinguish over one over the other? And that's the problem, that we don't have a unique set that you can nail it down to only one. Like you might solve, say, a set of 3 simultaneous equations with 3 unknowns. You get a unique solution. This is more like having 4 simultaneous equations and 5 unknowns. So look, I don't know. You don't have enough equations to uniquely find what each unknown is. So this is the fundamental weakness of cosmology and hence cosmogony. The weakness is inherent inability to accurately construct any global cosmological model. That is a model that accurately represents the structure of the universe at all times and all locations. And the reason for this is undetermination. And this exists in general relativity. It exists in any theories you might construct to explain the large-scale structure of the universe. And the reason is what I said earlier: you cannot interact with the universe. You are limited by your observational data. This is a fairly brief introduction to this concept of undetermination. It's evidence does not entail a particular theory. So this is the related problem. Ideally, we'd like one theory to explain the observations, but we might have 2 or more plausible theories to explain the evidence, and that they are equally good as far as we are able to test. Even worse, there might be a large range of theories, and we can't pinpoint one particular theory as suitable because they all have problematic issues. So I'd say this is exactly the problem of cosmology today and cosmogony, and I mean to include alternative theories in with the standard lambda CDM model. Karl Popper says, we can't tell if our theory is true, we can only tell if it's false. And that's true also of cosmology. We can only test to see if it is inconsistent with the observational data. So my second issue now, the question comes down to the Big Bang allegedly started in nothing, not even space, time, or energy. So there was nothing there, and we're not talking about the vacuum of empty space. We're saying that it started where there was no space or time or energy. And somehow the universe expanded out of some fluctuation of a quantum vacuum, but time did not yet exist, because time itself also came out of that quantum vacuum. You can't have a fluctuation in time in a quantum vacuum if time doesn't exist. So how do you know which laws of physics applied back then, and where did those laws come from? Those are the big questions that have to be answered. This is a quote from Paul Davies. Interestingly, it's in Is the Universe a Free Lunch? Quoted in there. Yet he says the laws of physics that permit a universe to create itself are even more impressive than a cosmic magician. If there is a meaning or purpose beneath physical existence, then it is to those laws rather than to the Big Bang that we should direct our attention. So this is really claiming now that the creator of the universe are the laws of physics from which that fluctuation of some metastable quantum vacuum arose, and then the universe expanded out of that. So this is the problem that many people have when they don't wish to accept the truth that the universe was created by a creator, supernaturally created, I'm talking about, outside of the existence of space, time, and energy. They then look for something in nature, in the creation itself, to be the first cause, to be the creator of that universe. And so in this case, it's coming down to the laws of physics. Well, as I said earlier, where did those laws of physics come from? Now, another problem is the fact, I alluded to this earlier, but it's impossible to form a star without dark matter, with one exception of having a nearby supernova, which is again a chicken and egg problem. The reason is because you have to compress the hydrogen gas cloud from which it is alleged the stars form beyond the limit where the thermal pressure of the cloud due to self-heating cannot be overcome by the external forces. And in most cases, without dark matter, it's only gravity. That's all we have operating. So dark matter is invoked as another form of matter that only gravitates but has no interaction with normal baryonic matter, has no electronic interaction. It has, so therefore it does not cause a pressure limiting effect on that initial gas cloud or the initial nebula from which the star allegedly condensed. And if you have no stars forming because of this basic physics, then no stars means no galaxies, which means no universe. Dark matter here has to be invoked on every scale: stars, clusters, galaxies, galaxy clusters, and the whole universe. And if you go back to the initial period post-Big Bang, you have to also invoke, without evidence, some type of a dark matter particle. The fuzzy axion is one of the latest ones, and it's needed in the early universe of just the right amount of mass. It can't be too heavy, it can't be too light. In fact, the fuzzy axion is one that is super, super light, but it's needed to get the early formation of galaxies. Now, it's a fine-tuning problem here, because if the density even of the axions is too high, then you'll get lots of black holes and you won't get galaxies forming, and the universe will collapse back in onto itself. So even the dark matter, or fuzzy axions, often called dark photons, they have to be of just the right properties, mass and density. to get this all to work. And this is a fine-tuning problem. So this is where you might invoke the anthropic principle, because if you can't explain it any other way, then well, the weak form of the anthropic principle would be invoked, which basically says, well, we live in this particular universe, we're here, therefore it's self-selection. You know, because we're here, therefore it had to have happened. That's the weak form of it. But again, this is just more pure fiction. Again, back to the CMB radiation. Now, it's worth remembering that the cosmic microwave background radiation is only measured locally. It is only assumed to be an echo of the Big Bang. And it was predicted, admittedly, it was predicted by Gamow after the Second World War. He started his prediction actually around about 5 Kelvin, because he and his students had access to declassified nuclear cross-sections, and they were able to do a sort of a Big Bang nuclear synthesis calculation of helium and hydrogen in the early universe. But just before the CMB discovery, Gamow had revised up his prediction to a 50 Kelvin, and which I would say was quite wrong compared to the discovery of it being around about 3 Kelvin. And then there's the famous axis of evil in this CMB radiation. It is a black body radiation, and it has very tiny fluctuations, temperature fluctuations across the sky, which are called anisotropies. You can map them or devolve them into spherical harmonic terms, and we have found that looking at these fluctuations, the first few order octopole and quadrupole and octopole terms, they have axes that align with the plane of the planets around the sun, the ecliptic. But it should be purely Gaussian. It should be purely random fluctuations. It should have, if it's from some Big Bang, which is now the whole universe, the alleged expanded universe, this radiation which should fill the whole universe, it should have no relationship to anything to do with our solar system or the plane of the planets around that solar system. There should be no preferred axes in this universe. So why is there this preferred axis, and why is it aligned with the ecliptic? Very good questions that would seem to indicate that it is not cosmological, but it is a local effect. And the data from both WMAP and Planck satellites confirm this preference of this weird axis or direction in the cosmos aligning with the Earth's orbit around the sun. So, in fact, the axis exists even in the higher than the octopole expansion terms of the power spectrum of the anisotropies. Why is that? Very, very strange effect. My suggestion is it is local, and it is therefore aligned to the to our solar system. Now, back to expansion of space. How does space expand and galaxies do not? Because the idea here is that galaxies are embedded in this expanding space, and the very famous rubber balloon analogy is often given, where the galaxies are like buttons glued on the balloon as it's blown up. But one would think that if galaxies are embedded in the space, the stars are embedded in the space, then as the space expands, the galaxies should also expand. And there is also this issue of, as the universe expands, we can look at the density of galaxies, say, in a volume of space, and we look at as a function of higher and higher redshifts. And where it does not seem to match, what we do is we invoke evolution. This is evolution of galaxies, meaning star formation, which also then means as they accumulate mass by collisions or by sucking it out of the intergalactic medium and star formation. So we turn up a knob of galaxy evolution as a function of redshift. So that's where the observations don't match at, say, high redshift as expected from the model. Then the knob, I call it a knob, for the evolution of galaxy size is turned up or turned down by the appropriate amount in order to get the expected galaxy density in that volume of space as a function of redshift I'm talking about, that the theory would require. So this is, again, another fudge factor. I hope that's clear. Then there is the issue of the singularity and the origin of the universe. Because there's no creator God in this case, the Big Bang model only begins by assuming time exists, and the laws of physics are already in operation. But as that Paul Davies quote mentioned, he's saying that the laws of physics are really the creator God in this case. So where did that come from? Where did the laws of physics come from? And how did time begin, or how did those laws of physics begin operating in time before there was any time? This is circular reasoning, where you have to impose this new creator on the universe in order to get it expanding out of the singularity and with the assumed laws of physics playing the role of the creator. It's a substitution of man's idea of a creator for the true eternally existing creator God who created the universe. And it's essentially man is putting himself into the role of the creator. So from this paper published, when it was published, 2014, the slide thing's covering that, I can't see it. So these authors state, we present such a proof based on the analytic solutions of the Wheeler-DeWitt equation. Once a small true vacuum bubble is created by quantum fluctuations of the metastable false vacuum, it can expand exponentially no matter whether the bubble is closed, flat, or open. And this is the Wheeler-DeWitt equation. The letter A there is the scale factor for the expanding universe. So this is literally replacing God, the creator, with this equation, which is really a representation of what they believe the laws of physics were operating in that initial expanding universe. So the laws are assumed in order to model the universe. Now, I've already covered this, but according to cosmic evolutionary thinking, our universe is the random result of the survival of the fittest universe in an infinite universe. And this is the multiverse idea. So if you don't want to accept a fine-tuning, a strong anthropic principle by a creator selecting the precise constants and physical parameters of the universe such that we get this universe we observe, then you have to move to a multiverse where we are living in only one part of an infinitely large multiverse, which has different laws of physics, like little bubble universes disconnected from one bubble to the next. And because we are here, the laws of physics and those parameters, those constants, physical constants, were just right for everything to evolve out of the initial expanding Big Bang universe and all the cosmic evolution that went with it, galaxy formation, star formation, and eventually life. So this is complete conjecture and is explained by this, to explain the fine-tuning that we do observe in the universe. As I mentioned, yeah, so the weak version of the anthropic principle is this type, which is a self-selection process. It's a sort of a observer bias, if you like. Then it's like saying, well, this must be true because we're here. Well, that was a rejection that there could be a creator, an eternally existing creator who created this universe. So if you accept the strong anthropic principle with the fine-tuning of all these parameters in a single universe, why was this universe so finely tuned, and why are the laws of physics such that they are? And we're not talking about a multiverse here. So, and the other questions are then, why did this universe, the only one, begin in such a low entropy state from which all usable energy could be derived? And the whole universe then is winding down. According to the second law of thermodynamics, it's like the universe was created in a low entropy state, high available energy, and has been winding down ever since. Other very important questions along this line are, why do we have the arrows of time? Because as second law proceeds, randomness or disorder, chaos, increases, and from our own experience, we know that as things become more disordered, we see a forward arrow of time. There are many arrows of time, but this is a very obvious one. And why is that? Why does that occur? Ultimately, we look back at the laws of thermodynamics, conservation of energy, first law, and the second law, which determines available energy, how energy is dissipated, and how work can be derived from that energy with an increase entropy over time. These are embedded in the fabric of the universe. These are laws that have never been refuted and that speak to a creator, in fact, speak to a design, that the universe is designed in every way ultimately for life to exist in it, but not by some random process in a multiverse, but by special design by a creator God who then created life on this planet. And we see this design all around us. So the theory of the origin of the universe out of a singularity requires certain initial conditions. I mentioned some of this already, talking about the concept of the axion in the early universe to produce the current observable universe, so it didn't collapse back into a whole pile of black holes, supermassive black holes. So it had to be not too smooth, that is, had to be homogeneous to a certain degree, and not too lumpy, right? It just had to, this is a fine-tuning issue. I'm talking about according to the Big Bang Theory. Because if it was too lumpy, it would have produced too many black holes and collapsed back into a singularity. And that's where the mass of the axion, of course, no one has ever discovered this dark matter particle. And it's worth adding, actually, there are no dark matter particles in the standard model of particle physics. They don't exist, so they have to be added by an extension of the standard model. But observations themselves do not support a homogeneous universe. Matter is distributed on large scales with an asymmetry of about 43% in opposite directions of the sky. That is the north and the south galactic hemispheres. It's not isotropic, and that's another problem. And there's also a whole host of other observations. For example, the rotation direction of spiral galaxies in the north and the southern galactic hemispheres, I'm talking about the universe, is not the same. There's an asymmetry between the two. So cosmic inflation is invoked to solve the problems of homogeneity in the universe. And I would think actually it doesn't really solve it too well, because even as larger and larger scale, large-scale measurements like Sloan and these very large galaxy surveys have been developing, we see a massive structures of cosmic webs. We see voids and webs. This is not a homogeneous universe, even on some of the largest scales in the universe. So modeling with the Friedman equation, where you assume homogeneity and isotropy, you have to then basically go to, you have to assume, you have to ignore the evidence in front of your eyes, because the universe is not homogeneous or isotropic. Okay, how did we go for time here?
Are you asking us how we're doing on time?
Yeah.
I would say we're doing pretty good. John, feel
Okay.
free to keep going. This is excellent information. We have a lot of audience interaction and engagement, and enough questions to keep us busy till probably same time tomorrow, Dr. Hartnett.
Okay, number 10. How did the Big Bang universe start to form galaxies? Well, the matter and the CMB radiation is not lumpy enough to seed galaxies, to start matter condensing to form galaxies. And this is part of the smoothness problem. Relates to, again, to flatness, but this is the smoothness issue. You need a certain level of lumpiness in the early universe to seed those galaxies. And I've mentioned already this ultralight or fuzzy axions that in the early universe have to be very finely tuned with masses above a certain value, about 10 to the minus 19 electron volt mass, which is incredibly light for a particle. I don't know of any particle that exists. There are no particles that exist with these type of masses. For reference, a neutrino has about a 1 eV mass, something like that. So what is often done with these type of problems is they search for dark matter particles as extensions of the standard model of particle physics. And the fuzzy axion, or the ultralight, is posited if it has exactly the right mass and certain initial conditions. Then it will initially help condense matter, because remember, dark matter doesn't interact with baryonic matter, but it gravitates, and therefore you can overcome the problem of the heating effects, the thermal effects, and the gas clouds being limited in their compression by using a deep potential wells formed by dark matter. And this happens on every scale for star formation, galaxy formation, clusters. On all scales, you need this dark matter that will overcome standard laboratory physics, standard thermodynamics, and get the hydrogen gas to condense into the stars, not just the initial first stars, but all stars and clusters and so on. And these are unknowns. In my own career, I actually worked on trying to detect a paraphoton. That's called a dark photon. That was, I think I have a slide. Let me see. I'm going to click on the slides here a little bit to see if I can find it.
I can put those up when you're ready,
Just
John.
a minute. Yeah, just a minute.
Take your time.
I had that exclusion space I showed you earlier. Here it is. Can you put that up?
Yes.
Can you see that? Okay, you see this is known as an exclusion space, and across the bottom you see the dark photon mass in EV and kinetic mixing parameter on the vertical axis. And all the colored regions are different lab experiments. Some of them are astrophysical, but most of them are lab experiments of various types to exclude candidate dark matter particles as in the extension of the standard model of particle physics. And I worked in around the megahertz range in a resonant cavity experiment looking for paraphotons. And you see the masses are tiny, absolutely tiny. The ultra light axion needs to have a mass above 10 to the minus 19 eV, which is way down in that bottom corner somewhere off the plot. So this is a lot of experimental time spent on this sort of experiment. You see on the right at the bottom, the xenon experiment that was recently concluded, where it was a large-scale experiment looking for, again, these are all dark matter particles of various flavors. I don't remember exactly. That one might have even been sterile neutrinos, but that's a heavier one. You can see where the mass is up at about 10 to the 1,000 eV. Now back to the presentation. So these are all unknowns. I mean, this is quite incredible when you think about it, that a lot of experimental physics in the lab, I mean, I'm not saying that these sort of research experiments shouldn't be done. I'm not saying that, because that's actually experimental physics. But all they're doing is getting null experiments. They're excluding the parameter space of finding any of these dark matter particles or photons. And it's been a total failure. They started initially with machos. I don't know if you remember the machos, massive compact halo objects, which are things like burnt out brown dwarfs or, these type of objects that were massive but didn't emit any light. But that was normal baryonic matter. That was all excluded. And then they went on to WIMPs, weakly interacting massive particles. And at the Large Hadron Collider, many particle experiments were run looking for a neutralino. A neutralino is the lightest, allegedly the lightest stable supersymmetric particle from one version of supersymmetry. I think after 10 years, they failed to detect anything. And that experiment then, well, I don't know if someone's reenacted another form of it, but that particular experiment was declared a null detection. So these were all searches for these extensions from the dark sector. Now, another problem is, why is the universe Euclidean? This is really the flatness problem, or space, Euclidean space. And it's been Euclidean right from the alleged Big Bang. And there's really no good reason for it. I mean, this problem started way back in the 60s. Now, they didn't have the cosmic microwave background sort of data then. It was really even before the precision of that type of data. That was where they were mostly doing galaxy counts on volumes of space. And it always seemed to be that the total mass energy density, which was largely a matter dominated, was around the critical density meaning a Euclidean space. And it was a problem back then. And part of the formulation of the Friedmann equation, which back in those days didn't have the cosmological constant, the formulation required for the fraction of the mass energy density in the universe to be very, very close to unity, which means critical and therefore Euclidean space. Now, various theorists have been developed since those times, and it is required then that once the cosmic microwave background radiation was measured and limits were put on the mass energy density from that, they found that the density could not vary from 1 by more than about 0.01, so 10 to the minus 2. Therefore, out of the Big Bang, initial singularity, it had to have changed by no more than a part in 10 to the 60 from that unity. So you could say the mass energy density evolved from 1 minus 10 to the minus 62 initially, just after the Big Bang, up to the current epoch of 1 minus 10 to the minus 2. And they were, the 10 to the minus 60, there were theoretical considerations based on inflation. So you had to preserve that Euclidean space through that whole time. I mean, this is quite incredible to think about this. But again, cosmic inflation is used by expanding the universe super fast. Then you are essentially flattening everything out. If you take a small area of space just after the Big Bang and expand that by a volume expansion of 10 to the 78 times, you essentially flatten it all out. And that's how it's invoked to explain this. Even so, I find these numbers mind-boggling, to say the least. I mentioned the monopole problem before. Too many monopoles should have come from initial Big Bang synthesis, nuclear synthesis. And so just by invoking cosmic inflation, you can stretch out the entire universe, and therefore the monopole density should go to very, very low. And this also includes things like cosmic strings and other weird stuff that has come out of some of these theoretical physics considerations for the early Big Bang universe. The horizon problem, I mentioned this already. This is a light travel time problem for the Big Bang, because different parts of the sky, we can look in opposite directions, and the thermal temperature that is the same, very close to 2.75 Kelvin, and yet these different parts of the sky on the opposite horizons have had no time to thermally equilibrate within the age of the universe. Not possible. And so, again, this is this idea of stretching out the very small piece of the universe in that early universe, 10 to the minus 35 of a second after the Big Bang, with this 10 to the 26 time scale factor expansion. Now, there are different versions of this, but they're all roughly around the same idea. So it's smoothed out all the problems in a sense. And besides, there's been no direct astrophysical detection of cosmic inflation. There was one point there with the BICEP 2 telescope at the South Pole where they were looking at the B mode polarization of the cosmic microwave background and made it such a claim. But I must admit, at the time I wrote an article and predicted that they would retract that very quickly, and they did. There were many others criticizing it, and it was quickly retracted because it was contamination from nearby galaxies had contaminated the radiation because they were sampling it too close to to have galaxies in the line of sight. So again, I think we've covered that. And then there's the discovery of the accelerating universe. Now that really should be put in commas as well, scare quotes, because it really, dark energy really comes down to a fit to a theory by taking a certain class of supernova and making the claim that particular class, the type 1a, all have the same absolute magnitude. So they have the same intrinsic brightness. But actually, we know that that's not true. And even the early papers by Rees and others at the time admitted that there's a distribution and that they had to employ a stretch factor to stretch the supernova light curves to make them fit on top of each other, and therefore they could argue that they are a standard candle, like a class from which you can then test your distance modulus theory as derived from the LCDM model. So that's one factor. And they've added back in the cosmological constant, but this time as something like the energy density of the vacuum. Well, what is that? It has an anti-gravity effect. Such type of energy doesn't exist in any lab experiment. In fact, it's so bizarre, one cannot even understand how you could describe it, because there is no type of energy that has a negative energy content. That's the best way, like an anti-gravity effect. It doesn't exist in the lab. But we now have dark matter and dark energy. These are two entities. And look, I have heard in different lectures some astrophysicists making the admission that these are placeholders for unknown physics. And I think that is a much more honest approach than saying that we've discovered a new form of energy, or in the case of dark matter, we've discovered a new form of matter in the universe. It's just that we don't know what it is. And in the standard LCDM model, that you have to invoke not only like a 20-something% dark matter term, as well as a 73% dark energy term. So you have like 95 or 94% of the mass energy content of the universe that we know nothing about. Totally unknowns. For an experimentalist, that's really a bad idea. That would tell me the theory's wrong. It doesn't fit the data, and therefore the theory should be discarded. Or look for new physics that is lab testable and could be reproduced, could be applied, I should say, on a universal scale. Now, earlier I mentioned this issue to do with underdetermination, and that there may be multiple theories to explain the same evidence. Some years ago, I got involved in an alternative cosmology. It was formulated by Professor Moshe Carmeli from Ben Gurion University. And it really was a phase space theory. When I say phase space, I mean it was space and velocity. The velocity here, it was an expanding universe, but the velocity here was really a redshift space. So it wasn't space-time. He called it space velocity. And we formulated a distance modulus, and I downloaded the data from Rees et al. And Astier et al. This data, and I tested the Carmeli cosmology against the same higher redshift supernova data that Rees et al. Won the Nobel Prize in 2011 for. And you see here, the first plot here, you see all the early lower redshift data points are from the supernova 1A from his data set. So I wasn't selecting any more than just taking all of them that they had published. And on the right, it's on a log plot of redshift, so you can see the lower redshift data a lot more clearly. And you can see that it fits the same data. But you'll notice that the green on the left here, the green dotted line, the matter density is 0.27. And that is like to include the standard concordance model data set of a 27% matter, baryonic plus dark matter. And you'll find actually that the Carmeli formulation fits much better for lower redshift, fits much better for lower matter density, mass density, than for the higher mass density from the concordance model. And the higher redshift numbers that range probably greater than 4, and in some of the earlier ones, are taken from the gamma ray bursts data that Schaefer had used. Now, gamma ray bursts are not technically a standard candle, and in their paper, they did a bit of sort of circular reasoning where they assumed their cosmology, which includes dark matter and dark energy densities, and then calculated a luminosity for the gamma ray bursts and put them on their plot. So I figured, well, if they can do that, I'll do the same thing. So I took their data and adjusted it for the Carmelli cosmology and put it on the same plot. And you'll see, so my argument is you have a different model that fits to the same data. In fact, it fits to a much better for a lower mass density universe than the standard model would. And in the Carmelli cosmology, there's explicitly no dark energy term. There is a vacuum energy term, if you like, but it's written into the physics. So it does have some new physics. But no dark matter is required. Now, I'm not saying I think this is the better model. That model also had problems, as does the LCDM model. It has problems. And I'm not under any illusion that this is the model. I'm not. And there's not time to go into that. But I'm trying to highlight here that there are alternatives, and there are many others. There are many other alternative models that can fit the same data. So this is back to this undetermination issue. Okay. Dark matter is required on all scales in the universe. And without it, you can't form a universe. And this is like a god of the gaps. But remember, dark matter started off by looking at, I think I've got a slide on this. It started off by looking at spiral galaxy rotation curves. Yeah. So these are a list of 3 non-cosmological arguments for dark matter. And this started back in the 30s, 40s, 50s, spiral galaxy rotation curves, which look something like this. The velocity of the stars seen coming out from the center of a spiral galaxy. You see the velocities increase. And then when you get beyond the limit of the visible stars, measuring with the 21 centimeter hydrogen line, you can see the gases swirling around that galaxy. And assuming a mass based on the visible light, so calculating the mass of the galaxy, or assuming the mass of the galaxy all resides in the optical, then you would get a curve like this expected from the visible based on Newtonian gravitation, Newtonian physics. But we don't observe that. We observe this, and we see many, many examples of this. So the question is this galaxy surrounded by a halo of dark, invisible matter that would then generate a rotation curve like that? Or is dark matter, again, another placeholder for new physics? So at the time, this is back some years ago now, I looked at this Carmelli physics to see what type of rotation curves you could get from that. And depending on the assumption of the mass density here meaning the optical visible matter, you could generate very similar, very typical rotation curves like seen here on the right. And 1 and 2 there just had different models of the fall off or the roll off, exponential roll off of the density from the center of the galaxy. So no halo dark matter assumed at all. I'm not saying that this is, again, remember, this is the problem of underdetermination. There are other models out there that also can generate solutions, or it can explain this type of rotation curve. And I want to just show a slide here. This slide. Donny, can you put that up?
Yes, there it is.
This is an article in Scientific American that does a fairly good summary of some work by, I think his name is Sari. Yeah, Sari. And his model, he's a mathematician, and he was able to generate rotation curves that are very typical. And he's got some publications there, Astrophysical Journal, American Math Monthly. You can see he's mostly a mathematician and the American Math Society. His model was that what's being neglected is stellar drag. So he simulates a galaxy, an n-body problem, which is like billions of stars, a billion-body Newtonian system. He simulates that and calculates the effect of the drag exerted from one star to the other, and he then gets these rotation curves. So this is like saying, in some sense, this is new physics. Well, he's not actually introducing any new physics. Back to the presentation. He's using standard physics and able to generate that without invoking any dark matter. So again, this is looking for alternative solutions to this problem without invoking dark matter. And so that's rotation curves in galaxies. The next one here is the dispersion velocities of galaxy clusters. And what that means, in clusters of galaxies, you see them moving too fast around their center of mass than you would expect from the Newtonian calculation. So you could say, well, maybe we haven't been observing those clusters long enough, and if you leave it long enough, they will disperse. I mean, we'd have to wait maybe millions of years to see that. But maybe instead, dark matter is invoked, invisible dark matter, to keep these clusters bound in a gravitationally bound system. I looked at the Carmeli cosmology of this problem and published a paper on that, and it also reproduces the observed dispersion velocities without dark matter, and in both rotation curves and dispersion velocities clusters, you get the Tully-Fisher relationship, which was found a long time ago, empirical relationship of the fourth power of the rotation speed of those outer stars or galaxies, in the case of clusters, is proportional to the mass of the galaxy or the cluster. And again, I'm not saying that that's the absolute answer. I'm offering that, saying that there are alternatives, just like the Sari paper, there was an alternative. Now, there's one other area which is often brought up as an argument for dark matter, and it's gravitational lensing of distant galaxies and quasars by closer galaxy clusters. Well, I agree that gravitational lensing is something that comes from general relativity, but then there is a really big issue to do with galaxies and and quasars. Quasars generally have much higher redshift, and they seem to be of a different morphology to galaxies. And the ruling argument is that quasars are super energized supermassive black holes at the center of galaxies and pouring out prodigious amounts of energy, often masking the host galaxy even sometimes. And that's the argument that these are very active galaxies in a sense. And there are active galactic nuclei, you could say, between these two extremes that might morphologically fit in a sort of a spectrum between them. So, but the issue, okay, just before we go on, in terms of explaining dark matter, in this case, we're looking at clusters, and there's a few examples. The bullet cluster is a very famous example where they see a bow shock, a shock wave, sort of the colliding clusters, and from the X-ray emissions, the claim is made that we see a separation between the dark matter or invisible matter region and the visible matter that's glowing optically. And so the argument is that you need dark matter to describe this. But as I said before, why not look for alternative physics? And there is this MOND, modified Newtonian dynamics. It is able to explain these type of cluster interactions without any exotic dark matter. It's able to explain it because it's modified the physics, the laws of physics, so that we have this description without any of this. I keep repeating this, the exotic dark matter that doesn't interact with normal baryonic matter, which is extremely bizarre type stuff. But getting back to the gravitational lensing. So this is an example here of an Einstein cross, where the argument is that there's only one quasar in the background of this object, and you've got a foreground cluster, and you have this gravitational lensing effect, which is a property of general relativity. You can do this calculation, and you've got the quasar light bending from around behind this, this cluster. But there has been a whole host of, decades, in fact, of work done on a different view of this. And that different view includes the idea that that we are, in many cases, we are seeing quasars associated with parent galaxies. And this is work that was had been developed over many decades, starting, I'm not sure when, but decades back with Holton Arp, and the idea where he saw on the sky low redshift galaxies with quite high redshift quasars enveloped in the plasma around them, and sometimes multiple objects like this, pairs in multiple pairs which have similar redshifts. And so a lot of work has been done around this hypothesis of quasars are ejected from active galactic nuclei, and that's, you see a matter formation process, which is a galaxy formation process. And therefore, the high redshift quasars are not at their Hubble redshift distance. They can be, if they're related. So example, I'm not saying this Einstein cross here may in fact well be an Einstein cross. I'm not denying that the gravitational lensing isn't real. I'm saying in many cases, though, it may not be the case, that there is a very high probability of many of these alleged Einstein crosses are pairs of quasars that have been ejected from active galactic nuclei. Just a minute. Just going back. I had something more to say on that. Yeah. Can you see this? Can you switch to this screen?
Yes, let me do it right now. Okay, we're good.
Okay, so going back a few years now, you should be able to see two papers listed here. These are in relation to this idea of a physical association between parent galaxies and quasar families. So you see objects like quasars, compact objects ejected from the hearts of low redshift galaxies. And there's a bit of a story to this that involves Holton Arp and Chris Fulton, which goes back about 2010. Chris Fulton had been working with Holton Arp on his PhD thesis on the reference here, number 2, the 2DF redshift survey. And he had been working for a number of years on this in his PhD when I met him. And he had been thrown out of his PhD because the supervisor left the university. And so I arranged for my university for me to take him on as supervising him with Holton Arp. And he completed his PhD by, I think it started in 2009. He completed by 2010. And at that time, he was already working on publishing this paper in the APJ, Astrophysical Journal, with Holton Arp. And we worked on it for years. I think it took 5 years. And it got published. It was a major battle through the senior editor, Vishniak, and eventually they accepted it for publication. And then that was 2012. And then we continued working on this through to 2018, where we got a second paper published which strengthened the first one, but we used the Sloan survey and the 2MASS redshift survey. And this strengthened the argument of galaxies, this illustration here, of parent galaxies having pairs of quasars aligned or in association with them. And we found in some cases within a 4 square degree area, 7 families of galaxies with of quasars associated with parent galaxies with a probability of it occurring randomly about a part in 10 to the 9. So this was extraordinarily a high detection for something that if you said, oh, it's just random. In fact, the detection algorithm found using sigma, like a detection algorithm, quantifying it by the statistical sigma. Normally 5 sigma is a detection, where we had some that were as high as 50 sigma detection. And we found that the redshifts of the quasars could be quantized or were quantized by certain discrete redshift values. So this meant that they were not at their Hubble redshift distance. They were associated with these low redshift galaxies. And that paper was, as I said, that was published in Astrophysics and Space Science. Chris is now working on a new paper associated with this, but looking at the spectra of even more galaxies and quasars in these very large databases. And he is he's tried to get it published in monthly notices, but he's not getting even past the editor. Back to the presentation. So you see, to publish something that explains the evidence, which this explains many of these type of associations we see in the sky, to get that past the editors alone is near impossible. But it has been done, as I showed you. We have achieved that. And this shows you, though, the massive censorship that exists in the peer-reviewed publishing environment when you come with an alternative, excuse me, to the standard Big Bang interpretation. Now, I want to move on to one more issue that I think is very, very significant because matter and antimatter, how would you say, based on the concept that all matter arose out of an initial Big Bang, which just started at like 1 trillion degrees or something, and it's all thermal energy, and then eventually it cools, and that energy condenses into particles. There should be an equal amount of matter and antimatter, the particle and its antiparticle. The problem is, of course, in the universe, that is not the case. In fact, the amount of antimatter in the universe is absolutely tiny. So there's this enormous asymmetry. And another reason the ultralight axion has been postulated is to try to solve this matter-antimatter asymmetry. So the idea being that when the axion disintegrates, when the axion self-annihilates, in case I think if its axion is bosonic, then it is its own antiparticle. It will produce an asymmetry of matter and antimatter because the universe doesn't have large regions of antimatter. In fact, the amount of antimatter is tiny, it's scarce. However, the idea has been that if they detect dark matter, then it could be used, like dark matter may be axions or axionic or even other types of dark matter particles as extensions of the standard model of particle physics. Then they could use that as a marker for the presence of the how would you say a proxy, of how much dark matter must exist, which has never been observed. So if you could detect an axion, in other words, which has this property of when it self-annihilates, that it can generate an asymmetry between matter and antimatter, then you could say well, that amount of dark matter must exist out there somewhere because the matter-antimatter asymmetry we observe in the universe indicates that it must exist. I don't know if you get that. It's kind of a circular argument for the existence of the unobserved dark matter. Oh, okay, I've got one more. 17 must be a lucky number. The mass of the universe, depending on how you calculate it, is in disagreement between the different approaches, using type 1a supernova versus the Planck cosmic microwave background data. You get a different mass for the total mass of the universe. And therefore, an extra neutrino, relativistic sterile neutrino, sterile meaning it doesn't interact with normal matter, is often called dark radiation and has a mass around 1 eV. So it's nothing like the ultralight axion, which is called dark photon, but it's a much more massive particle, a relativistic particle, and that can then be used to explain why we measure that the different masses, because we're not accounting for the sterile neutrino in the mass total mass budget. However, having said that, not only are there dark photons and dark radiation and various types of dark matter particles proposed, also we now hear of dark planets, dark stars, completely comprised of dark matter, dark galaxies, and even dark intelligent life has been suggested. I know that sounds totally crazy, and I'm not even suggesting that many astrophysicists would even believe that, but people have made those suggestions. And I just say this is more fiction. Yeah, so I think that should be enough in one slab here.
In one of hopefully many sessions, Dr. Hartnett, that was an excellent presentation, comprehensive, which is the way that we like it here on Standing for Truth. And if I hypothetically believed in the Big Bang Theory before watching that and knowing about all of these challenges and problems with the Big Bang, I don't know how anybody being objective could look at those problems and still hold to the Big Bang as a viable theory of origins, which brings me to my first question. Maybe this will help set the foundation for some questions and points of discussion. John, you pointed out many problems with the Big Bang. You stated that the data doesn't fit the theory. So my question is, does this mean the theory should be thrown out? In other words, we have a lot of pieces of evidence or data points that perhaps a specific viewpoint has a difficult time explaining, but it's not necessarily a data point that precludes that position. Do at least a couple of these problems preclude the Big Bang, as in make it impossible?
I think the short answer is yes. But as I said also, if you're honest, dark matter, for example, or dark energy, just talking about one of these, if you're honest to say that this is a placeholder for unknown physics,
right,
then that's okay, because we now have a problem to try and understand what that is. But if you're saying that the that unknown is supporting the model, and that therefore the model is correct, and this is often how it works. In order to determine or test the standard model, the standard model parameters are assumed to test it. There's a lot of circular reasoning here, and you often have to look into the details, and you'll find that that is the case. Yeah, so fitting, for example, to the type 1a supernova data, as I showed you, an alternative model could fit that, right?
Mm-hmm.
And that will fit it without dark matter. But there was a intrinsic energy density term for the vacuum of space. Well, there are alternative models out there now looking at large-scale structure that are quite different, that test. So I'm just going to see if I've got a slide here that take some new observational data and test the model and compare it to a new proposed model, and this is happening. I just haven't. There was one I had here. Where is that? Yeah, I haven't found it. But with the latest data on very large scale surveys and the cosmic web, a new model has been proposed that includes the voids. It includes the cosmic web structure and all the voids. And it has in the model, instead of like a cosmological constant, that he invokes a changing parameter, like a cosmological constant, but it's changing as a function of redshift. And also he has tired light. So the redshift of the galaxies varies because of light, the transit time of light through the vacuum of space, and they lose some of their energy. He has that in the model, and he's able to fit to all the data. I think that's called CCC plus TL or something like that. He's able to fit to all the data without any additional parameters like dark energy and dark matter. But he does have these added parameter, this control parameter. So he's changing the physics, trying to solve this problem. But it goes back to the issue that it's possible that in all the models, and there are many models, there are many in the alternative cosmology community have different models. It's possible that none of them describe the visible universe. And there may be good reason for that too. And that is that the universe is the physics that we understand about the universe maybe not the same everywhere. I mean, the part of the cosmological principle is that the physics of the universe is the same throughout the entire universe. And without that principle, you can't do cosmology. You certainly can't do standard Big Bang cosmology, because that's what it's based on. But what if that's not the case? What if the physics is different in different parts of the universe? Another issue is, what if those galaxies, like spiral galaxies, rotation curves and all, what if they are actually dissipating? You know, and so the argument, the comeback there is, but they're billions of years old. But how do you know they're billions of years old? Because, again, the circular reasoning is kind of obvious, and most people wouldn't even consider it. They would just completely reject it. But what if the universe is actually young? And when I say young, I mean like only 10,000 years old. And so there's not been enough time for clusters to dissipate or galaxies to dissipate. And all of the observations we're making today, which don't fit the standard known physics, is telling us that we've got the physics wrong because we've got the model wrong. All the models are wrong. And therefore I include the standard Big Bang model is wrong. It never happened. There was never a Big Bang.
Since a theory, Dr. Hartnett, is supposed to be supported by processes like observations, experimentation, research, making predictions, and those predictions are supposed to be tested and proven to be true or accurate, things about the future. I'm curious, is it still accurate to call the Big Bang theory, or has it failed? It sounds like what you just said, it has failed as a theory.
I would say unequivocally it's a failure. No experimentalist would ever accept a theory that has so many contradictions.
Right.
And they come up all the time. And so what are invoked is, what do they call them? They're called additional hypotheses, and they're added on. They're like patches. They're continually added on. But no physical theory should be patched like that, because it's telling us something, that the basic underlying theory is wrong. And it's the Friedman approach. I did a lot of work on Friedman and a lot of work on alternative cosmologies to try and understand this, but I don't think you can save the standard Friedman equation as a description of the large-scale structure of the universe. I think we have to look elsewhere for new physics.
You mentioned, John, in your presentation, Carmeli physics. This is new to me, but I found it to be very interesting. And therefore, correct me if I'm wrong, is this proposing a fifth dimension, 5-dimensional?
Yes, that's correct.
Okay.
Just a minute. The last book, Carmeli died, I think it was about 2009. I think it was, he died. And he had written the last book. This is it here. That's probably all backwards, is it? Or,
no, looks good. No.
Okay. That's the last book. He died before he was able to finish editing it. And so with his grad student, PhD student, not student, so she was a postdoc, sorry. We worked on it together and did all the contributions were there, and we finished it, and it was published. This is published by World Scientific. So that has a very good, how would you say, analysis of all his ideas there in his theory. And it was really started with a 4-dimensional space velocity theory. The velocity was the velocity of the expansion of the universe. So there's an expanding universe model. But he never found a 5-dimensional solution. I'm talking about for the full general relativistic 5D, space, time, and velocity. He never found a solution to that. And those data fits I showed you were based only on the space velocity model, which is, in physics, we would call that a phase space because there's no time dependence. He argued that when you looked at the universe, you really weren't looking at a time slice, or maybe another way of saying it, when you looked at the universe, you looked at an instantaneous time slice through the whole universe, but you're only seeing it seeing the universe as a function of redshift or velocity of expansion. And that was the basis which he developed the idea around. I say all that because he never found the full 5 dimensional solution for the universe. And that was a major weakness of the problem. So even though in a restricted area, it actually could describe a number of different observations, it had other problems elsewhere. For example, he had a special theory that did include time, but it was inconsistent with his general theory. And you know, from general relativity, if you turn the knob of matter density down to 0, you can get special relativity out of general relativity. They're totally consistent one with another. Carmeli, his was not. He couldn't find that. I looked for a long time. I looked at higher dimensional models, theories, to try and see if we could find a solution to it, because there was a very nice part of it that worked very well. But I gave up on it quite some time back, because if a model doesn't work in certain areas, and you can't rescue it without creating these additional ad hoc add-ons, then it's time to abandon it. And I did. So I abandoned that. And I think that's where the Big Bang should be.
Right.
That they should abandon it, because if they can't explain the most fundamental things like what is expanding space, or what is dark matter and dark energy, and don't forget, for 40 years or more, 50 years maybe now, they've been looking for dark matter particles. I showed you that exclusion space. That's a lot of manpower. That's a lot of experimental energy spent for a very long time. When do you say it can't be done? You know, as a good example, when they did that experiment at the Large Hadron Collider, which was over about 15 years, but effectively it was 10 years of experimental time, and they didn't detect the lowest, the lightest or lowest mass supersymmetric particle. A lot of the scientists working on that gave up. They agreed that it was a failure. But this is the but now. There was a certain group that refused. That they said, no, that's not good enough. We will continue. We still believe in it, and we will continue. And I'm sure they are continuing today. So a rejection through experiment is not even enough to convince the most ardent, diehard believers in the theory.
Wow. So if I could say this, then Sam, we'll hand it to you for a question. There's so much to discuss and elaborate on your comprehensive presentation, Dr. Hartnett. And so I see very frequently, and we've seen it here tonight during your presentation, where you've put forth these major problems, one of them being the matter antimatter problem or challenge. And many pro Big Bang theorists, they will concede and say, okay, yeah, these are problems. We don't have answers to them just yet. We're looking for answers. We're going to continue studying. But oftentimes they will resort to saying, okay, well, why should we give up the Big Bang? Because what's the alternative? Creation, a supernatural explanation. So in a way, the response is a form of scoffing. And so, Dr. Hartnett, I'm curious, what do you think the best response would be to somebody who holds to the Big Bang, but they refuse to give it up because of what the alternative could be?
A very good question. From my perspective, I find it very easy to put my trust in a creator, because I see design. I see design everywhere in the universe. I see it very specifically, of course, in the solar system. But the person who is putting all their, and it's faith, putting their faith into the Big Bang, is it because they cannot conceive of a creator God? Is that the reason why it's so difficult for them to do it? I think comes down to, and I often say this comes down to a worldview issue.
Yeah.
This doesn't come down to science. It doesn't come down to evidence. You can argue this evidence on that evidence, but it comes down to what your worldview is, what you believe, and that worldview then is sort of like glasses that you see through to see the evidence. You interpret the world around you through that worldview. Unfortunately, I know there are many people who believe that in cosmology that you can find evidence that will establish it, will prove it. But if anyone uses such words as proof, they don't understand how science operates.
Right.
Mm.
Yeah, that's a great answer. In science, we don't prove something,
Yeah.
right? We come to the best possible explanation, come up with a hypothesis, try and refute it. So is science more so about disproving things? And
Totally about that.
Yeah.
Totally. Yeah.
So,
but Donny, the history of science also tells us that the scientists themselves don't follow that.
right. Worldviews and those points you made, very important. Sam, did you have anything you wanted to say in response to that, or anything that you heard during the presentation?
Yeah, I do. I have a lot of stuff that I'd love to talk about, but I know we're not going to have time tonight anyway. So hopefully we get you back on again. What do you think? What do you think is the proper way to understand the redshift?
Okay, that's a really big question in itself.
Yeah.
Okay, and that actually goes to a lot of those issues, including what I talked about, galaxy quasar associations. It's interesting to note, number one, that I have a friend who's been compiling a database on redshift mechanisms, and most people know of about three. Gravitational redshift, which is experimental physics. We observe it like satellites, GPS satellites, and so on. We even do time corrections for the GPS satellites and so on. Then there's Doppler motion, also well established in the laboratory, absolutely irrefutable. It's just observed in all sorts of places and situations. And the third one most people know is this cosmological redshift, which only, and I'll use the word observed, only observed in the universe. Now, the redshifts are observed. Absolutely, they are. It's the interpretation for the mechanism behind it, and expansion of space is not directly observed, but that's the one most people think about. And they have, as I mentioned earlier, they have the wrong idea generally of the idea of galaxies moving away from each other through space. But that's not the concept of cosmological redshift. It's the space itself expanding. Now, we do see local motion. We see Doppler motion. For example, the Andromeda galaxy is blue shifted towards us, and there's a few other galaxies in our local cluster that are blue shifted towards us, but that's virial motion. That's motion within the cluster. We would call that Doppler motion. Whereas a center of mass of the cluster is supposed to be moving away from the center of mass of all the other clusters around us in the whole universe.
Would an example of that be as something is moving away, perhaps there's a rotation where an arm is coming towards us in a minute, or in a moment, but ultimately it's going to correct as it moves away?
Yes, that's quite true. So if you're looking at the rotation of galaxies, you're looking at the stars and the gases. You look at one side of the galaxy and you make all your observations into the center of mass of the galaxy. So even though you're looking at one side or the other side, you then subtract off the net red or blue shift of the galaxy, and you will see blue shift on one side and red shift on the other side as the galaxy is rotating. So that's all we actually see. We only measure the Doppler shift of the galaxy. So you imagine as the galaxy rotates toward you, you see a red shift. As the galaxy, I'm talking about the stars, as they move away from you, you see a blue shift as they move towards you and a red shift as they move away from you into that center of mass motion. And that's also true all around us in clusters of galaxies. The redshift component we would measure from Doppler motion is only the radial component. That's the component toward or away from us. So that's either blue shifted toward us or red shift away from us. That's all we can measure. Now, I've mentioned those three redshift mechanisms, but there are many, many more that are proposed. There are many different types of processes in gases, all sorts of different processes, even like relativistic transverse redshift, lots of different mechanisms that are not even considered. And so my friend who maintains a database of these different mechanisms, look, I haven't looked recently, but I remember the last time I looked, he had 39 different mechanisms that could produce a redshift. I think pretty well all of them are experimentally verified in the lab, but cosmological is not.
Yeah, I mean, the Bible does mention, I believe, about 17 times that the heavens are stretching out. So it would certainly be consistent. I don't know that it follows from that expansion can be extrapolated back to a singularity, especially with some of the problems with physics that you've mentioned, and there are certainly more.
I would actually argue, Sam, and look, I as you know, I did a lot of work on expanding universes in cosmology, but I would argue now that the biblical evidence, those 17 verses, do not describe cosmological expansion. And so, quite a few years ago now, I went back and had a look at all of them, and I looked at them in the context of the Hera, those verses that the prophets were describing, this is the word of God through the prophets, and the similes or the references made in those verses were often things like putting up a tent or spreading out a curtain. And so I looked at that and I thought, well, when you put up a tent, does it stretch? Does the fabric stretch? And even if you only talk about looking back to Redshift 7 or so, that was about the highest redshift galaxy we had at that time. So that would be a stretch factor of 7. But if you were going back to the last scattering surface, a redshift of 1100, you're talking about an expansion linear scale factor of 1100. And if you talk about inflation, you're talking about 10 to the 26, or pick any number you like. Well, the rubber sheet analogy, the rubber balloon analogy, possibly could have those type of expansion factors, but putting up curtains and tents and all this sort of stuff, those Bedouins traveling through the desert and all those places, they had no such concepts. There's no way they could have ever read those verses and got any idea. And I don't believe there's some hidden secret message in those verses. God was speaking to them in the context of their own knowledge.
Sure.
So I actually no longer believe those 17 verses have anything to do with cosmological expansion. Instead, I offer alternative interpretation. God was just telling him He made the heavens. He created the heavens. He did it like they would put up a tent or they would put up a curtain. He created it that way. And that's why I no longer believe it. And I one time went to, at the time it was Albuquerque, sat down with Russ Humphreys. He and I worked on a lot of these things together, expanding universe models, creationist models. These were attempts we made. And I told him, because he was on about his second, or part B of his second version of cosmology. And I said, Russ, you can't assume cosmological expansion. And we went through all the verses together, looking at the Hebrew and the original meanings. And he said to me, very humble man, because he said, you're right, you convinced me. Just like that, amazing. I never expected it. I thought I'd get a big argument from him, but no. So he then started working on static universe cosmologies from that moment on.
If I remember correctly, one of the first books within a series of books that I read when I first became a young Earth creationist, Dr. Hartnett, was your book, and I still have it, Dismantling the Big Bang. Since that time, have you changed your view on certain things like what we're talking about here? From my understanding, white hole cosmology and gravitational time dilation. In terms of things like, and I know we could probably, and hopefully we could, do a whole show on distant starlight. Have you changed your views in many ways on what best explains distant starlight?
Yes, very much. I think any scientist worth his salt should be willing to look at the evidence. And remember, we're only developing models, theories and models. And you should be willing to discard them where necessary and develop new ones where necessary. So yes, over time, I saw holes in these different things, and I could explain to you some of the history of that. Might be a bit boring though, but when you start to see where the model has a problem, it should be rejected, and a new model should be sought to try to fit that. So so the white hole idea, it was very interesting, and that started with Dr. Russ Humphreys, but his initial white hole model required a deep potential well that was inconsistent with the observational data. So what that means is we look at, like I said, we look at Andromeda, and Andromeda doesn't really have any redshift. It's blue shifted, Doppler motion, but you can't even if you believe in cosmological expansion, there's no redshift. So that means in his model, where our galaxy was somewhere near the center of that gravitational potential well, the bottom of the well would be flat, essentially flat. And you can't get any time dilation from that gravitational redshift, because in a flat well, they're all at the same gravitational potential. And so he moved on beyond that when we realized that was a failure of that model. But it spurred on other ideas, and work came into his next model. And then when I showed him the universe, I can't say that the universe is not expanding based on scripture, but I can say scripture does not require it. The scriptures that people were basing it on do not require cosmological expansion. Anyway, we spent many years going through this process, and that's how it should be. That's how science should operate. Always looking to preserve the truth of the scripture, but looking for models that are consistent with it.
Therefore, and I appreciate that answer. Therefore, when we are confronted by critics of young Earth creation, Dr. Hartnett, And they, even though you pointed out that they themselves, you've pointed out in the past that the critics have a distant starlight problem themselves with the early conditions of the universe. They do like to, right.
Yeah.
And they do like to challenge us on how can we see, if the universe really is 6,000 years, how can we see distant starlight that's billions of light years away? What at this point, Dr. Hartnett, do you believe is the best way to counter that challenge?
I think I note that you had Jason Lyle on your show.
Yes.
Not so long ago. Did he speak of the conventionality thesis, the one-way speed of light?
Yes.
Spoke on that?
Yeah.
Okay. I think that's the best solution. That's the best answer. I spent a lot of time with Anne Ross Humphreys on looking at time dilation models. And I'll just lump them all together because we went through quite a few different iterations and different ideas. But I believe we have not found a solution there. However, I do believe that what Jason Lyle started to promote from about 2003 or something like that it was, when he was doing his PhD, it was under a pseudonym, is the conventionality thesis that is essentially telling us you cannot measure the one-way speed of light. You can't measure it. It's only chosen by convention. Einstein chose his by convention in about 1907, and we're free to choose it. There is no preferred one-way speed of light in the universe. The universe does not require any particular speed. Therefore, it's a convention. There's no way to refute a convention because it's not an experiment. So people have come up to me for many, many years, but what about this? What about this? What about this experiment? Someone's on the moon, someone's on Earth, and send a light signal. And they have all these complex ideas, but all of them come down to sending a signal out and back. It always becomes a two-way measurement. So in short, because the only light we have coming from the universe is the light we see in our telescopes or with our eyes at the Earth or in the solar system, it's all the same thing, is we can't measure the speed of that light coming in. So we are free to choose that it's infinite speed. There's no delay. And so we see the entire universe in an instant, you know. To impose upon it that there's a delay at traveling at the two-way speed of light, the round-trip speed, is actually imposing something, a convention, a different convention, imposing it on the observations without proof. And this is an absolute fact for 120 years or something now. People have tried to refute the conventionality thesis, which is ironic, really, because it's a convention. And you can't do it because you can't refute a convention.
The conventionality thesis, Dr. Hartnett, is that essentially saying that we're seeing light from even the furthest reaches of the universe in real time. We're seeing it as it is.
Exactly. Yeah, in real time. That's right. Yeah.
Have you seen any good rebuttals or critiques to that model?
Well, it's no doubt you have gone to rationalwiki.com. Have you been to that site?
Oh, yeah.
Under one-way speed of light. It's beautiful because they admit the whole concept is correct relativistic physics. And they say it's a trick they say it is correct, but it's a trick, and Lyle uses this trick. It's kind of begrudgingly saying that there's no way to refute it.
Right.
So I think that is the best testimony of all. That's like in a court of law when you have what they call the witness for the other side. You know, they're testifying on your behalf, and I think that is powerful evidence because it is fundamental physics, and that's
Right.
all it is.
This is all consistent with the physics of Einstein.
Absolutely, yeah. There's a really good book by Max Jammer, Jammer, and it's called maybe it's called The Simultaneity of Time or something like that. It's an excellent book because it gives you the whole history of its development, and the experiments were done over the last 100 years, the theoretical developments, Einstein. And it's not just about the speed of light. It's about measuring any speeds, like measuring the speed of a massive object like a test particle moving away from the observer. So it doesn't apply to just photons. It applies to any particle, and you have to use the correct equations of motion depending on your choice of convention, and that also refutes a lot of the arguments when people they state an argument against it by assuming the two-way speed, the isotropic speed of light, and then say, well, how does that work with this? It's because they've used the wrong equations to describe the physics. So it becomes a circular argument in a way. If you assume c, the canonical speed of light, you are assuming the synchronized clocks separated by a distance, and that's the isotropic two-way speed of light. And so you've got to be really careful about that. So by choosing the correct physics, which is the physics of Einstein, but I'm saying it's the correct physics, even Maxwell's equations have to be formulated in the correct frame of, in the correct way, using the Reichenbach parameter, which codes for the choice of the convention that you're using. You know, Lyle chose a certain convention, right? Einstein chose a certain convention, but there's an infinite number of choices between the two that you could choose, and all are correct physics. For people who don't quite get it, there's a really good way to think of this, and that is transforming from one frame of reference into another frame. Like you could say, and this is done all the time in astrophysics. If you're looking at the solar system, you could look at it from Earth-centered celestial frame, the center of the Earth, or you could transform your physics over into the sun-centered celestial frame. So the physics will be the same, the equations will be different. So they'll be totally consistent with each other, even though the equations look different, the underlying physics is unchanged. And that's how it should be. Physics doesn't change depending on your frame of reference.
Very good answer, Dr. Hartnett. Sam, over to you.
Yeah, there's a secular YouTube channel called Veritasium, and they put out a video called "Why No One Has Measured the Speed of Light." And they're not interested in this conversation that we're having, but they did a really good job of explaining with visuals why we can't measure the one-way speed of light. I would recommend anyone to watch that video.
What's it called?
Well, the YouTube channel is through Veritasium, and the title is called "Why No One Has Measured the Speed of Light." They've done a really good job. You know, I found that most critics, they just want to argue against this rather than actually try to understand. It's not that difficult to understand.
No. No.
But there's a worldview issue, as we've already discussed.
Yeah, there is. And I think the worldview issue has this other added feature to it, that even young Earth creationists have a problem with this for this reason, is that somehow they believe, or they've come to believe, that Einstein's physics is the correct one. So therefore, Einstein's choice of isotropic speed of light is the only truth, some sort of absolute truth in the universe. And maybe it's uneasy to accept that we can't know. And so they will compare everything in that frame of reference, that the speed of light is the two-way speed, the canonical speed, and everything else has to be tested on that basis. And their brains are so wired. And I've had a lot of trouble at times trying to convince people, no, that is a choice of a particular convention. Yeah.
Well, while we're on the subject of light and stars, you did talk about why star formation is a problem. And so, and I apologize if you've already answered this question, but the question here is, do we see stars or observe stars forming today, or is that process just inferred?
Yeah, I'd say the latter. It's inferred, and it's inferred based on the ultraviolet luminosity coming from galaxies. But often that ultraviolet luminosity is calculated based on redshift. So some of the JWST high redshift objects, galaxies, they're called, what are they called? Little red dots or something like that. Because the James Webb Telescope is tuned to the infrared in the micron range. But if you translate that by scale factor, redshift, back into the rest frame of the galaxy, assuming that that's all correct, then it will be in the ultraviolet. So then they will say that that's evidence of massive star formation. So number one is there's underlying assumptions that are actually unprovable and subject to these other issues to do with redshift and even the redshift distance. You know, this whole idea with quasars that could be close and associated with parent galaxies. Well, they have very high redshifts, and therefore their redshift doesn't indicate that they are very distant. Have I lost my point? So I would say, no, we do not observe star formation at all. What we are seeing is what a lot of the secular astronomers are called they call them, like, what are they, nurseries, star nurseries and this sort of thing. And what they are seeing is these type of emissions from high density regions. But to see a star born would be to see a hydrogen, neutral hydrogen gas cloud collapse down under gravity and get to sufficiently high temperature that nuclear fusion could switch on. I argue that that process is impossible because of the Jeans limit. When you get to a certain gas density and under compression, the thermal energy of the cloud prohibits any further collapse of the cloud. And again, this is where dark matter is invoked without evidence. It has to be invoked because otherwise there would be no stars, and therefore stars must form this way. and have dark matter that gravitates but does not interact with baryonic matter, means it doesn't interact with all that gas in the cloud. But creates a deep gravitational well that the normal matter can fall into with the dark matter, of course, and then switch on, get hot enough and switch on to become a star. But that process is not directly observed. It's only the conditions they see in these nurseries, star-formation nurseries.
On the topic of dark matter, Dr. Hartnett, there's a question here from Andrew Cumming, who would hold to Big Bang cosmology. And he's wondering, if not dark matter, where does Dr. Hartnett hypothesize this extra gravity is coming from then?
There's a bit more needs to be added to that. What circumstances is Andrew meaning? Is that for star formation or for galaxy formation?
I think that's a good question. I'd have to get a clarification from him. This came in a little while ago when you were in your section on dark matter and dark energy. I think it was slide.
I believe, and I could be wrong, but I do believe it was in the context of stars forming, because you did talk about that. You did talk about star forming for a while.
Okay, so I never mentioned my view of star formation other than when I was referencing a creator of the universe. Well, I believe that all stars, as all galaxy clusters and so on, the whole chain, are all supernaturally created because there is no other way to overcome the known laws of physics. And so God supernaturally created them that way. It's worth adding, in all the simulations, these simulations are primarily at the larger scales, like galaxy cluster and so on. They always start the simulations with an overdensity in the model. They have to have an overdensity to get sufficient gravitational, anyway, another way of saying sufficiently deep gravitational potential well to get the rest of the matter to gravitate or to fall into that. So all simulations are like this. And on the fine granular scale in galaxy formation, you have star formation. And so the way that is done is in the simulations. Say for a galaxy, you add a dark matter content in the galaxy. I'm saying that didn't happen. God supernaturally created those stars in all their forms, and they switched on day 4 of creation week, which was less than 10,000 years ago. That's the argument I'm making.
There seems to be a clarification. It may have been about galaxy rotational rates and densities.
Okay, so if it's on galaxy rotation curves, then there are a number of possible alternatives. And one of them is a really simple one, is that it's not extra gravity at all. There's a number of possibilities. One of them is that we are observing the universe on such a sufficiently short time scale, less than 10,000 years, and we see it in real time, and there hasn't been sufficient time for the galaxies and the clusters to disperse. A sort of how would you say, an alternative modified version of that is that there is a fifth force in the universe. Now, generally, in the 80s and so on, the physicists look for a fifth force. Casimir effect was one place they looked. But there's a lot of evidence in the scripture, so I'm basing this on a biblical worldview, that God has a fifth force in the universe. And this force, and I put that in commas because it's really a power, a sustaining power of God that he will use to sustain his creation. Now, this works against the processes of the second law. The second law basically tells us all systems will tend, isolated systems will tend to a state of greater randomization. That's heat flow, downhill, energy's lost. This is all well-established physics. So, but God also talks about in the future of establishing his heaven, and I'm speaking here of the physical heavens, that they will be forever. They will last forever. They'll be eternal. For that to happen, he would have to reverse the process of decay, of increasing entropy. So, in my view, the timescale that we don't have millions of years. We don't have hundreds of thousands of years. We have sufficiently short timescale left before major changes like this occur, and God establishes his eternal heaven. And then he will bring his sustaining power up, like bring it back. Oh, okay. I need to go back a little bit. This sustaining power was in existence in the creation, the initial creation. And at the curse, God simply reduced some of that sustaining power. The second law of thermodynamics was always operating. All the laws of physics were operating right from the beginning. But God regenerated the chaos or the randomization prior to the curse. So that's why in the garden, they could look at it as a true paradise, that nothing would hurt or destroy or decay. But at the curse, that decay didn't change that law. He just reduced the sustaining power, and the decay became more dominant. Well, if that is reversed, then also that's true of all the stars and galaxies in the universe. I think there's strong evidence that the curse was on the whole universe, and that God will reverse that in due course. That's as part of his creation. Another alternative is looking for new physics, like that Sari, the mathematician, the drag, stellar drag for spiral galaxies, to look for alternative physics to explain what we observe. There have been other people who have done piecewise modeling on spiral galaxies, where they looked at density as a function of radial distance, and they found that using a numerical analysis, that they could generate galaxy rotation curves without inventing any halo dark matter. That's just based on the visible, the light, the matter coming from the visible matter in the galaxy. So I think there's a lot of work that could be done along that line, along looking at alternative physics, and of course modified Newtonian dynamics. I mentioned that about the bullet type clusters. They're able to explain them without dark matter. They are also able to explain galaxy rotation curves without dark matter, but that is a modification of Newtonian physics. So they're changing. That's a new physics approach, and I think they're more genuine than making up stuff that doesn't exist in the standard model of particle physics.
What would be a good response to this comment, Dr. Hartnett, that is a defense of inflation? And so Andrew Cumming, I appreciate the interaction and the feedback. And so he says inflation has made specific predictions that have been verified through not just those listed, I think referring to an earlier slide. We're just not sure yet which specific model of inflation is the correct one. What would be a good way to respond to that, John?
Well, that's cart before the horse, unfortunately. Again, this problem of underdetermination. Now, I'm not sure what he's referring to as specific predictions, but if he's talking about the solving the problems of monopoles, horizon, flatness, homogeneity, these type of things, that's really not a prediction. That's, if anything, a post-diction, that is invoking inflation to solve existing problems. So I'm not exactly sure what he means by that. But the other problem is he's right. There are different models of inflation, and they're not. It's like arguing over a straw man, multiple straw men, and you're arguing over which straw man is the correct one. What if none of them are? You see, so
Right.
It's really a worldview issue again. You believe that the observed universe is described by the standard model plus inflation, possibly plus some theory of Big Bang nuclear synthesis and some putative developing quantum gravity theory, and you cobble all these together. But that's because you have a prior belief to describe the universe without a creator, without that basis. And so I say you can never say which is the correct one in his question here. You cannot say it because you would have to rule out every other possibility. And even then, it's still wrong because you can only refute. You would have to refute all, I don't know, X million other models, unknown number.
It seems kind of strange that they would want to hold on to an inflation model as opposed to going back to a steady state model where that doesn't have theistic implications of a beginning.
Yeah.
I'm not sure why, because they were shocked when they found when the redshift was first observed and interpreted as a beginning. That's
right. In fact, it's very ironic. I point this out to people in a talk anyway I did years ago. The early there was the developing camp between Hoyle and what's his name, Bondi, Gold, the steady staters, and then there was Gamow and a few of these other guys who were the new guys on the block. They were the developing Big Bang proponents, and this is back in the 1960s and 70s. Well, those guys were considered the new the young Turks who were promoting these new theories, and they were called the evangelicals. I don't know if you know that. They were called the evangelicals because of the Big Bang origin in time, and that was considered to be a sort of a negative slur upon them. As you know, Fred Hoyle named the Big Bang. He said, they believe in some kind of Big Bang. Unfortunately, it stuck. So this just shows you again the worldview issue that is at work here. But both camps were non-believers in a theistic creation. They weren't, Yeah.
Is it largely a refusal to question the greater theory itself? because as you're saying, it's a worldview issue. What's the alternative?
Yep.
Creation.
That's exactly right. In fact, I've heard that. I've heard that as a response where they say, well, what else is there?
Right. Yeah.
Like, I even heard it where they say, this is the best, what is that expression? The best dirty shirt in the laundry or something like that.
Yeah.
The cleanest dirty shirt in the laundry. Yeah.
Right. Dr. Hartnett, as we start to wind down, I was wondering if, and I'm going to put up your slides here, I wanted to interact with, I believe it's point 16, the matter and antimatter asymmetry problem. And I put your slides up on the screen. I was wondering if from your end, does it still allow you
it's there. Go back to 16. I can see 17.
Oh, there we go.
Okay. All right.
So this one I've seen many times over the years. One of the many problems, but this is a problem that I hear even the most militant critics of creation and most adamant proponents of Big Bang, when they are forced to engage the matter antimatter asymmetry problem. Firstly, to reiterate why this is a problem, is it essentially that the prediction of the Big Bang, that we should find a somewhat equal ratio of matter?
Equal amount. Yes.
And yet we find an overall.
That's correct.
Okay. And so since we don't find that, we're not even close to finding that expectation. I've heard many of them concede that at this point, they don't even have a good answer. They're working on it. And so would this be one of those problems that in many ways is enough to preclude the Big Bang theory from being true? As in they need to discard it and they need to move to something else, John?
Yeah. This really applies to early universe Big Bang nuclear synthesis. So, but yes, I agree. In fact, if you go back far enough, there was a time, maybe this is going back to the 70s or something like that, there was a belief that there were large regions of the cosmos where it was antimatter. You know, I'm not sure, I can't remember specifically if anyone suggested antimatter galaxies, but I wouldn't be surprised. And that is because self-annihilation of matter in particle physics, we know it's pretty well always matter antimatter. Yeah. There's a thing called CP violation, which occurs in weak nuclear forces, and what is it, in something like what is it? Forgotten which particle decay, beta decay, or something like that. So I think that was like that very tiny asymmetry that occurs there. They were looking for an asymmetry in the early phase of the universe where the energy from the Big Bang would form into matter and antimatter with a slight preference to matter, and then re-annihilate, leaving only what we would call matter. In other words, all the antimatter is re-annihilated. So that's the asymmetry that you would like to look for in some particle physics process. And nowadays the axion is being searched for, because axion, the ultralight axion is, one version of it proposed as a boson, which is a charge, a force carrier, not a charge carrier, a force carrier, that might help this process of getting this asymmetry working in the early Big Bang universe. It's still all emperor's new clothes.
Right. Yeah.
Even the emperor doesn't exist. I mean, in that story, the emperor was real. In this case, the emperor's not even real.
Yeah, the emperor doesn't even exist.
Yeah.
Dr. Hartnett, this is
So-
fascinating material. And it really is a great time to be a biblical creationist. More and more when you see this kind of information presented. I see a lot of comments, just to leave no stone unturned as much as we can in one session here. I see a lot of comments from critics and those that hold to the Big Bang. They'll say, well, we're the ones that predicted the CMB. We predicted it before it was discovered, before it was established. And so that is a point, a big point for the Big Bang being true. Is that true? Are they overplaying their hand? And what's a good way to engage?
Okay. Yes and no is the answer on that. I actually already gave them credit for that at the beginning of my talk, that the prediction of the CMB is like a tick in their favor. It is. But there is a bit more to the story, because some people would argue that it was Herman and Alpha who were Gamow students. They had access to hydrogen helium nuclear cross sections, and they were doing these calculations on like at very high temperatures, forming how would you say, distribution of early elements: hydrogen, helium, deuterium, lithium. Maybe they throw in beryllium nowadays. And so some people argue then, at that time, it was really a post-diction. In other words, they already had access to what they would expect the thermal temperature to be. I mean, this was at very high temperatures. I don't have the numbers off the top of my head, but it only cools down to 3 Kelvin because of the massive expansion of the universe. So the argument, look, I'm giving it a half tick as half a prediction, because they did have information on the temperature, the physics of the temperature of the, let's say, wasn't a nuclear explosion in the Big Bang, but that was the idea. It was built around that type of an explosion. And so it's a post-diction in that case. I think in 48, Gamow had predicted 5 Kelvin locally at 0 redshift. And by the time of Penzias and Wilson, when it was at 65 or 66 or 65, he had revised that up to 50 Kelvin. So again, that's where I think it's, I give him that one, even though he didn't quite get the temperature right. So
if they get if they get half a tick or even 1 tick on that one, right? Say you just give it to them, but then they've flopped on 10 others. What does that say about
That's the point I was making. So you don't judge your theory on the successes. You judge it on the inconsistencies, the failures, the fudge factors, all the auxiliary, this is auxiliary or post or ad hoc patches you have to add on.
Right.
That's the failure of the theory.
John, what's the significance of the axis of evil? We've got a few questions on that, and you talked about it in your presentation.
I don't have a slide easily accessible to me. I should have grabbed one on that. So the radiation from space all around us, it's ubiquitous, is this 3 Kelvin black body spectrum. But if you take off the black body curve, which is very smooth anyway, you get what they're called anisotropies. These are the thermal fluctuations. And if you then look at those thermal fluctuations in terms of, you can expand them in spherical harmonics. So the first one is very strong, very large. It's the dipole term, which has a strong redshift or blue shift component to it. And so the argument for that term, this is the lowest order term, which is the strongest term, is the motion of the solar system through space. That's an interesting discussion in itself, because that would have to be against the background, cosmic microwave background, right? But what is more puzzling is if you take the quadrupole, octopole, and higher terms. So what that is like looking at those fluctuations. Like the quadrupole term has 2 hot and 2 cooler regions, and it has 2 axes running through it. The octopole term has 4 hot and 4 cooler regions. So they're like the larger, these are describing these larger sections, the average temperature over a sphere of this temperature. If you say average over the sphere over like a quarter of the sphere, you'll see a warm region and a cool region over the quarter. If you go then to the octopole, you go to smaller size and you'll have 8 regions, 4 warm and 4 cool. Well, these regions have axes because they're aligned. They have axes run through them. And if I'm not mistaken, there are, octopole will have 4 axes and the quadrupole has 2. And I think it's 5 out of those 6 axes all align with each other, and they align with the plane of the ecliptic and even the equinoxes, where the summer and winter equinoxes, where the sun is directly over the equator. That is totally bizarre, because the cosmic microwave background radiation is meant to be Gaussian, meant to be totally random. It's like you sitting in a giant cavity, and the radiation is coming from every direction in the sky, and it's fluctuating on a random basis. Then why would it have anything to do with the plane of the orbital plane of the galaxy? That's taking off the dipole term, which you might have an argument for because of the motion of the solar system, of the Earth, the solar system, the whole solar system moving through space. But the other terms have these alignment, these axes. It's just very bizarre, and it's I don't have an explanation other than to say, well, maybe this is my best guess, is because the radiation is local, that we are living inside a black body, a cavity that has a perfect black body source. And I have a conjecture then about that, which is in my new book, which hopefully will get published one of these days. And that is the black body source was the initial thermal radiation from the creation of the Earth as a body of water. God created the Earth as essentially became a ball of water that rapidly cooled to about 3 Kelvin. So that emitted that thermal radiation through space in 3 dimensions, and it would travel out to only thousands of light years in the frame of reference of the Earth at the center. And now I'm admitting this is conjecture, this is a speculation, but it's consistent with the idea of a biblical creation with the Earth at the center of that creation.
It's consistent. And so this pattern of temperature fluctuations basically in the CMB.
Yeah.
Big Bang theorists agree or concede that this is in many ways a challenge to them, because doesn't it go
Correct.
against?
So when the WMAP data came out, they saw that in the quadrupole and octopole expansion terms. And then they thought, oh, by the time the Planck satellite, which had more sensitive microwave sensors, that would all vanish, it would disappear, and it would be just all random. But when Planck came out, the data was even better. And you can go to, I don't know what the higher terms are called. You go to, N16, 32, and so on. And they found these axes in all of those higher order terms. So it's in all of the data, in the fluctuation data.
Wow.
I don't believe anybody has an answer for it.
Yeah, it's great information. Sam, any last questions from you, brother, on, I got to say, John, time flies by when you're having fun discussing the Big Bang. Hard to believe we've been going for a few hours, but it makes me that much more excited, brother, for round 2 and hopefully 3, because there is a lot to discuss. But I do want to give you, Sam, the opportunity for a final question before we wrap things, if you had one, before we wrap things up for tonight.
Yeah, I do. Those temperature fluctuations, are those problematic? I guess I'm wondering why there wouldn't be an equilibrium of temperature on their timeline in the CMB.
Okay, so this is again about inflation, right? What we observe is near perfect black body spectrum. But this is the argument about the smoothness, the horizon problem, because it wasn't expected. Because if you imagine if you have you have an explosion, it's probably the wrong word, but you have initial temperature thermalization of the early universe at a trillion degrees or something, then the expectation is it's going to be random fluctuations around that. It's going to be chaotic. And as the universe expands, this is pre-inflation, those areas separate, and there's insufficient time, limited by the speed of light, for them to equilibrate. So if you look at one horizon, compare it to the other horizon, the light we see from that horizon has never had time to mix with the light from the opposite horizon. So why is it such a perfect black body spectrum? And that's when inflation is invoked, because if you take a tiny area of that initial Big Bang universe, that initial early universe, and stretch it out, this is spatially stretch it out, then the temperature fluctuations over that small area, which were not great, they were small, they get stretched out over the whole visible universe. So that's the solution to the problem. But if it's a perfect black body spectrum, normally in physics, a black body spectrum is from a source that's internally in equilibrium, and so it's like I'm not sure if I'm getting at your point there. Can you clarify if I'm answering that or not? If you're getting to the
Yeah, no, I was just wondering if or how those temperature fluctuations were or were not, or are or not consistent with their model, or if they would be problematic.
Oh, it's absolutely problematic. Yeah, but not at not every problem that's arisen from it is inconsistent. So if you look at the cosmic microwave background radiation and you do a spectrum of those anisotropies, then there's certain peaks in that spectrum. This is of the anisotropies, which are like 1,000 times smaller than the primary dipole term. So they would look at those fluctuations. You can create a spectrum of those fluctuations, and based on modeling of the early universe, they then say we will fit to this part of the spectrum a component that's due to the matter content, which is dark matter content. And so they then explain the shape of the spectrum based on their modeling of the early universe with dark matter and the radiation density and so on. I mean, dark energy was not relevant really in the early universe. That really came into play later on. So they derive from the CMB radiation a dark matter term. That they constrain that within certain range. So if I can sort of turn this around, they take the data and they take the model and they try to find a solution to that model based on that observable data, and that generates that you need a dark matter component. You see what I'm saying?
Yeah.
That requires a fudge factor as well. But there's lots of other types of analyses which require modeling in the early universe that results in later large-scale structure of the universe, like bubbles and filaments and elements that form from freezing in some effects of the early universe, and then it gets manifested as seeding of galaxies in the later universe. So this is all part of the modeling. People spend their PhDs and they do a lot of research on this. There's enormous effort into this. And I only say, well, what if they're wrong? What if all those fudge factors don't exist? What if they're completely fictitious? It's like, again, it's the emperor has no clothes,
So those fudge factors, Dr. Hartnett, they are akin to rescue device after rescue device. Would it be accurate to?
Yes, I think so. Yeah. I mean, we have to be even-handed.
Right.
As I said, we have to allow for the possibility of new physics, but generally that's correct. They're generally rescue devices. And I think they become more and more of a rescue device when you've exhausted all possibilities to explain them, and you refuse to give them up. And you refuse to give them up because of a prior worldview that you hold.
Amen. Oftentimes it's not an evidence issue. It's a heart issue. We know some are willingly ignorant. They'd rather worship the creature than the creator. Romans 1. I want to sneak this one in because it is such an interesting topic. And again, perhaps we can dedicate a whole program to it. But earlier, because a lot of people have clarifying questions on the conventionality thesis to answer the distant starlight challenge. And so when somebody asks, okay, when I see the light from the sun, then, because from my understanding, the sun, the light emitted from the sun is about 8.3 light minutes away.
Correct.
Are we okay? So according to the conventionality thesis, are we seeing that just in real time as well? Or is it actually taking 8 minutes to get to us?
Okay, so Donny, you need to get educated. It's a convention. So the simple answer to that, under the ASC, the anisotropic synchrony convention, the light arrives instantaneously. Under the Einstein synchrony convention, it takes 8.3 minutes. You understand what I'm saying? It's a choice.
Right. It's your choice.
It's a choice.
It'd be like
You
picking
make the
kilometers
choice.
or miles. You know, it's your choice.
It's exactly right. It's a choice you make. And there is another issue related to that, which I don't know if you thought about, but modeling of the sun, the photons coming from the fusion reactor at the center of the sun do a random walk. And it's been calculated takes about 180,000 years or 150,000 years. Don't quote me on the number, but it's a large number. And so some people might say, well, how does the light? God created the sun on the fourth day. How did Adam see it on the 2 days later? Well, you could argue that there's a long random walk, but you could also argue that during creation week, there was a lot of creation of the universe in the form that we see it today. In fact, I would say pretty well all of it was created in exactly the same form that we see it today. So though it may take that photon 100 and whatever thousand years to walk its way up to the surface, to the photosphere, and then take the 8.3 minutes to get to Earth under the assumption of the Einstein convention, God created it all instantly, fully operating and fully functioning on the fourth day of creation. And so think about it on the second day of creation, God made the foundation rocks. So therefore he made the crystals in the rocks. And when the light from the sun on the fourth day hits the earth, the crystals are responding to that light. The plants were made on the third day, so they also responded to the photons coming from the sun on the fourth day. So in their frame of reference, not that the plants were scientists or anything like that, but in the frame of reference of the plants, you could say that light also arrived instantaneously in their reference frame. But it doesn't matter, because under the Einstein convention, 8.3 minutes is nothing much. The plants waited 24 hours all night to get the sun. And but the whole argument about one-way speed of light is a convention worldview argument.
Right.
And the physics of the universe operates whether or not you choose one convention or the other. And like I mentioned earlier, it's often better to choose the convention that helps you understand the physics the best according to what you're looking at. And so the isotropic speed of light is extremely useful in most physics, because it simplifies those equations. But when it comes down to this issue of distant starlight and the timeline laid out in the Bible, we should look to the scriptures to see what the language in the Bible is really referring to. And I'm sure Jason talked about this, but the language of creation is, I would call it the natural language. And it often speaks of, like in the creation process of the stars, the way God spoke was like implying it could be seen immediately from the earth.
Right.
God spoke, it was created. He doesn't say there's a delay of 1 million years before that light arrives at the earth. He speaks it into his existence. When he spoke, there's verses like saying that the creation stood up together. I mean, it's like instantly God spoke it into existence. So that's the natural language. That's the language of speaking in the present. Just like we speak in the present, when someone on the distant hill turned a light on, a flashlight, and you saw the light go on, you say, oh, I just saw it go on just now. Now, I know the travel time, even under Einstein convention, is very short, but it's the language that we use. We speak in the natural language. And it applies to sound, even though sound is a lot slower. It's the same thing. It's still the same convention on the speed of sound. Speed of anything is convention by convention. And we often say that, right? When I heard a thunderbolt, it just happened now, but actually, if you go back on 1,100 meters per second and push it back in time, well, it would have happened so many seconds prior to when you heard it, when the thunderbolt or the clouds or whatever the mechanism is that caused it occurred. But under ASC, we can simply say it happened when we heard it. And that's natural language. It's all in the present now. The corollary to that is to say there is no past. The past doesn't exist. It's gone. There's only the present. We live in the present. We can't see the past. There is no past. It's gone forever.
Dr. Hartnett, that is an excellent, helpful answer on an important issue. And this has been a very informative program, Dr. Hartnett. I really do appreciate your time and also your endurance, as this has been an information-packed program, that is for sure. And you look like you're ready for another 3 hours, brother. So
I don't think so.
I appreciate you doing this. To the audience as well, as always, we appreciate the feedback, the challenges, the objections. We said at the beginning of the program, we do like when our critics are here, because we do want to answer your challenges and, of course, hopefully plant some seeds, right, Dr. Hartnett? It's not always about winning arguments. It's about winning souls and standing for truth. And so, Dr. Hartnett, I do want to hand it to you. Again, thank you so much for all the time that you've given to us for tonight, and also all of the years and years of work and study, because clearly you know your stuff on this issue. So I do want to hand it to you for some final words and final thoughts that you'd want to leave Sam and myself with, but also our live audience tonight.
I'm very encouraged to see a forum like this, and that you asking and looking at these issues. I think the most foremost issue in all of this is to understand that it's a worldview issue. It's not who has the best evidence. And I'm not denying that you can develop theories and models to explain that evidence, but it's a worldview issue, because your worldview is the filter by which you judge everything. And I think I take my worldview from the biblical, the history in the Bible, the Genesis account, and I don't find that there's anything in that other way around. I don't find anything in any sciences that I've studied that undermines the veracity and historicity of the Genesis account. Yeah. Thanks, guys.
Amen. Dr. Hartnett, again, great final words. Praise the Lord for your work and this opportunity that we've been given to discuss these issues for the amount of time that we have. Sam?
Thank you. Donny, just before you go, could you put the slides up again there?
Absolutely.
Just to the last slide, just so people, if they want to study some of this and look for stuff I've spoken about, they can go to johnhartnett.org, but that will direct them to biblescienceforum.com. That's my site. And you can put in search terms in the search box. There's actually a lot there. that people might find useful and interesting. So thank you very much.
My pleasure. Thank you. I've got your BibleScienceForum.com website linked in the description box. So for those in the live chat, if you've enjoyed what you've heard from Dr. Hartnett tonight, do check the description box and have a look at that website. I've spent a lot of time going through your articles and your material, Dr. Hartnett, so I can tell people that, yes, there is a lot there on a good variety of topics as well. Sam, appreciate you tonight acting as our co-host. I hope you enjoyed this as much as I did. Sam, let's hand it to you for some final words, brother. Thanks again for doing this.
Yeah, hey, my pleasure. Thanks for letting me tag along. Dr. John, you're a wealth of knowledge. I learned a lot. I'm gonna have to go back and listen to again for sure. And so, Donny, thanks for having me on. I appreciate it. God bless you guys.
My pleasure. Definitely the kind of program you're going to want to watch a few times. Bring a pad of paper, a pen, and make a lot of notes because there's a lot there. Dr. Hartnett, God bless you. Sam, God bless you. And to the audience, God bless you all. Thank you so much for tuning in. Standing for Truth is out.